I'm Hugo Caselles-Dupré and I will present our paper Symmetry-Based Disentangled Representation Learning Requires Interaction with Environments. We'll do first a quick recap on Symmetry-Based Disentangled Representation Learning, or SBDRL. Then we'll present our contribution, and then we'll talk about discussion and future work. So the motivation is disentangled representation learning, where we try to isolate factors of variation in data. But the problem is that disentanglement needs a proper definition, which is not the case at the moment. So SBDRL tries to define what disentanglement is through the use of symmetries and group theory. In their definition, they use an underlying word state W, and they use symmetries like translation or rotation. And they try to build a representation Z such that the effect of transformation on W will be the same as on Z. So that's the definition of symmetry-based representation. And then they define disentanglement as the fact that the symmetries can be decomposed into different subgroups that do not affect each other, such that a transformation will affect only subgroups, subspaces of the representation Z. So this is the definition of disentangled representations in SBDRL. And in their paper, they learn representation using only still observation. And we try to make a point that SBDRL requires transition and not still samples. Because, for example, the transformation can affect the world state in different ways regarding what are the physics in the world. So we are able to prove that using Theorem 1. And for practical options, we show that there are two options that you can do to learn SB disentangled representations. So the first one would be a-la world models, where you would learn a representation and then you would learn how the transformation affects this representation. And then you can also do end-to-end learning strategy, where you would learn both at the same time. We show that both approaches works in practice in a small toy example, which is pretty much the same as they use in the Higgins paper. And then we also test if the learned representation can be useful for learning downstream tasks, which is the case in our example. So there are many open questions about SBDRL, and one of them is how do you learn the subgroups of transformations? And maybe we can associate this with actions. That's one of the possible ways to go. So in conclusion, a formal definition of disentanglement is needed. SBDRL tries to define one, and then we make the point that and prove that SBDRL needs transition and not still samples to be learned in practice. So our code is available on Colab and on GitHub, and make sure you check out the paper on arXiv. Thank you.